Detecting events in aircraft trajectories, rule-based and data-driven approaches. Access to large amounts of aircraft trajectories opens a wide range of perspectives for monitoring and for post-operational analysis of air traffic performance. We address in this presentation the automatic identification of operational events associated with trajectories. These include not only commercial flights, but also any aircraft equipped with an ADS-B-compliant transponder, helicopters in rescuing operations, aircraft doing their share in firefighting, zero-gravity test flights, and military operations like in-flight refueling or landing on an aircraft carrier. We introduce here different rule-based, empirical, deterministic methods on one hand, and statistical, data-driven, machine learning methods on the other hand, to detect a selection of these events. The goal is to compare candidate methods and to determine which of the approaches performs better in each situation. My name is Xavier Olive, and this is a joint work with Chinze Sun, Adrien Lafage, and Luis Pazora. In the full paper, we first present a taxonomy of the events we claim to be able to identify. These include occurrences of specific missions, for example, firefighting operations, flight inspections, or aerial surveys. Then navigational events, common with commercial flights, for example, holding patterns, fuel dumping, direct to, and finally the identification of flight phases. These events are not necessarily mutually exclusive. This test flight, for example, can be labeled as a succession of climb, descent, and level phases, or as a sequence of fugurids, or, as a whole, as a zero-gravity test flight. External sources of information are a major asset when one wants to properly label events. Aircraft registration databases bring insight about the capabilities of specific tail numbers. The structure of the airspace aircraft evolve in cannot be bypassed when identifying navigational instructions, for example. Open sources of such data are listed on atmdata.github.io. As this is an open initiative, please do not miss any opportunity to contribute. Depending on the final application, aircraft databases may be enough to identify specific missions. Regarding the CV fires in California last September, we extracted here trajectory information for aircraft operated by CAL FIRE. We display here trajectories together with fire locations provided by the Fire Information for Resource Management System. We implemented here an ad hoc method to extract non-straight trajectory segments. Then, we can build such a heat map to display firefighting operations in California during this particular week. Call signs can be helpful as well, as this toy example shows. Non-straight segments for trajectories of aircraft relaying TV signals during the Tour de France 2020 make up a beautiful data visualization, nothing to be ashamed of, even when put next to the official map. Aircraft broadcast a specific type code in ADS-B messages when on ground, the on-ground boolean in the OpenSky Impala database. This feature is knowingly unreliable to detect the exact landing point. On the left-hand side, on-ground information is not consistent with vertical rate information. This is unusable to determine the exact point of landing. On the right-hand side, the altitude profile for the aircraft shows several landing attempts on the Pacific Ocean, actually an aircraft carrier, but the on-ground flag is desperately set to false. These first basic recreational examples aim to show that the simpler approach is often good enough. Detection of navigational events is arguably the most relevant success story for rule-based detection, together with fuzzy logic for flight-based labeling. Flight management systems are precise enough for a comparison between the track angle of the trajectory and the bearing to a navigational point to efficiently infer the max point in a flight plan or direct-to order. The same method applied to runway thresholds successfully finds the runway an aircraft aligns on. Combining this approach with flight phase labeling, we can distinguish go-arounds, that is, to runway alignments separated by a climb phase, from parallel runway changes on the left or circle-to-land maneuvers on the right. Now comes the core part of the presentation. We want to compare here rule-based and ML-based approaches on two specific use cases for situation labeling. runway changes, and holding patterns. Long story short, corner cases give a hard time to both methods, but trying them both helps finding and understanding them. The implementation of a rule-based runway change detection function is very direct. Iterate on pairs of successive segments of trajectory aligned on a runway and yield them if no climb phase lies in between. We published in 2018 a functional principal component analysis-based runway change detection method aiming at assessing contributing factors to a risk of runway excursion. Late runway changes being combined with late changes of glide plan have been identified as potential contributors. Data preprocessing included the selection of the last 8 nautical miles of trajectory before the runway threshold, followed by a resampling of the track angle values. FPCA projects on each component the principal variation modes detected in the dataset, while the first mode models the first alignment with the runway. Following modes correspond to actual runway changes. We constituted 2 datasets of rule-based detected situations to be compared with FPCA-based situations. 139 trajectories were detected by both methods, but let's focus our attention on the 44 trajectories detected by the rule-based methods and missed by FPCA, then on the 23 trajectories detected by the FPCA but missed by the rule-based method. Among trajectories detected by the rule-based method only, we plot here the distribution of distances between the aircraft and the runway when it initiated a runway change. The blue part of the distribution corresponds to very early runway changes occurring before the 8 nautical mile threshold we used to prepare the FPCA dataset. So, the ML model could not possibly detect runway changes on part of the trajectory flown out of its scope. The red part of the distribution, however, is more intriguing. The FPCA seems to have missed the very late runway changes. When we look at variation modes in detail, we see that the fourth mode in yellow actually corresponds to these late changes, and our criterion selected only the second and third modes. The rule-based method here helps refining the implementation of the FPCA-based method. The rule-based method missed identifying this flight as a runway change, probably because it never really aligned on 3 to left. However, the analysis of the track angle and altitude profiles shows that the first intention was to align on 3 to left before being cleared to 3 to right and catching the new glide plan. There is probably a way to refine the rule-based method implementation, adjust thresholds, and catch this flight, but we may as well acknowledge that no method really surpasses the other. A holding pattern is a maneuver designed to delay an aircraft already in flight. These are commonly implemented in terminal maneuvering areas or in flight when the crew needs to run through checklists. There is a clear definition for holding patterns, which are usually designed around a holding fix, with specific rules explaining how to enter and exit the racetrack pattern. While this definition seems very strict, there is in practice a lot of variance in their implementation, and simple rule-based methods around self-intersections or parallel tracks are very easily challenged. Also, being able to identify and label the start and end of an holding pattern would fit the needs of many performance analysis, mostly around airports. This image displays various situations easily mislabeled by rule-based detection methods. An aircraft shooting photo views for aerial survey yields a trajectory made of many self-intersecting parallel segments. Military air tankers perform refueling while flying more oblong racetrack patterns in specific designated areas, but depending on the application, we may want to not have them as true negatives, or at least filter them out of the dataset. On the other hand of the scope, trajectory A is delayed with a short right-hand turn that we probably shouldn't label as a holding pattern. Trajectory B prematurely flies out of this quick holding pattern, easily labeled as a false positive. Trajectory C raises a question about the final timestamp we want to set on this holding pattern. We present in the full paper the highlights of a possible detection method. First, decompose a trajectory along a sequence of sliding windows. Let's call them samples. Rescale the track angle for each sample for all trajectories in a dataset. Then project the samples to a third-dimension space and follow the path of each trajectory in the latent space. Projection can be defined linearly with a PCA, as in this figure, but neural networks may be trained to fit a nonlinear projection operator. The desired property for two similar samples is that they become neighbors in the latent space as well. The implementation of a proper model, including a projection operator and a proper classification model in the latent space, is currently being validated on larger scale data. For now, commonly mistaken trajectories are properly separated from the true positives. In-depth details are expected to be published in the near future publication. Large-scale analysis of trajectories requires flight phase, pattern, and procedure identification so as to bring useful insight to situation awareness, monitoring, and decision-making systems. We presented first how very simple rules based on aircraft or call sign identification can be enough to extract relevant information. External structured knowledge about flight plans, airspace structure, procedures, and operational practice is essential to implement relevant rule-based detection mechanisms, whereas statistical machine learning-based methods are of great help when access to such information is sparse. Rule-based methods are easy to describe. They present robust and explainable results, but are subject to many parameters to adjust in order to select corner cases only fitting part of the implemented definition. Machine learning-based statistical methods, on the other hand, excel at extracting knowledge without or with poorly specified operational input. However, significant expertise is essential to interpret the results. Based on these observations, the author would recommend statistical methods when a detailed definition or knowledge about context and external constraints is missing. Based on results and extracted information, rule-based methods should be considered, implemented, and performance of both approaches should be reviewed without bias.